the previous lecture, we focused mainly on the vaporization of a liquid and how the value of the enthalpy of vaporization, delta H, and the resulting vapor pressure and boiling point are impacted by the magnitude of the intermolecular forces operating between the molecules in the liquid. Now, in this lecture, we will expand our scope and look at energy changes involved in all phase changes from solids to liquids to gases. In the previous lecture, we discussed the equilibrium specifically between water and its vapor, and we showed it as in this diagram here, H2O liquid in equilibrium. These would be equilibrium arrows with H2O gas or H2O vapor. We can now expand our coverage to include the solid form of water or ice, and we can label the process occurring during each phase change. So what I have here is on the far left, solid water or ice, in the middle, liquid water, which we'll just call water, and water vapor or the gaseous form of water. We're going to put arrows between these different phases, but we're going to color code them. So when you see an arrow in blue, it represents an endothermic process, meaning it's a process that requires an input of heat energy. And any arrows in red represent exothermic processes. Those would be processes in which heat energy is released to the surroundings. So if you go from solid to liquid, water, we of course call it melting. It's also called fusion. If you go from liquid to gas, it's called vaporization. Now each one of these arrows and labels are in blue because each one of these processes or phase changes requires an input of energy from the outside. In other words, you need to put energy in or heat the ice in order to get it to melt to water, and you'd need to further add heat or energy to get water to vaporize to the gas. Going in the other direction, if water vapor undergoes condensation and becomes liquid water, that heat energy stored in the gas is released to the surroundings, and so the arrow is red. It's an exothermic process. Likewise, if liquid water freezes, heat is removed from that system, or in other words, heat is released, and so it's an exothermic process. We can also shortchange this process by going directly from a solid to a gas. That would be called sublimation, and of course would require an input of energy. And we could go directly from the gas to the solid. That would be called deposition or vapor deposition. And of course that would be an exothermic process because it would entail release of energy to the surroundings. Now many times in general chemistry textbooks, you'll see these energy changes depicted in a little different way, basically on a vertical axis. So we have a diagram here where the vertical axis is the energy of the system, and you notice the solid is represented as having the lowest energy, liquid a little higher energy, and gas having the highest energy. And just as in our diagram going from left to right up here, we need an input of energy from solid going to liquid. We would need more input of energy going from liquid to the gas. There'd be a release of energy going from gas to liquid or from liquid to solid. And of course, the input of energy needed for sublimation or the release of energy for vapor deposition is also shown in this diagram. Now, as implied by this qualitative diagram, there's no real numbers on it, it's generally considered true that for all substances, not just water, the energy difference between the solid and liquid form is significantly less than that between the liquid and the gas form. Now we can try to make a qualitative description of why that might be using the cartoons below, where you see a pictorial representation of a solid and a liquid and a gas. And if you note in terms of the spacing between the molecules, a liquid looks a lot more like a solid than it does a gas. So it's not surprising that it takes a smaller energy input to turn a solid into a liquid than it does to turn a liquid into a gas. Now, it's possible to calculate the total heat energy absorbed when a substance is heated and or undergoes phase changes. For example, below is a generic heating curve for water. We call it a heating curve even though it doesn't appear to have any curves on it. They're all straight lines, but I digress. A heating curve for water where a known mass of water starts at minus 25 degrees C in the form of ice, that would be at point A, and after a time interval of continuous heating, that time interval of continuous heating would be the x-axis. This 25, or excuse me, the ice at minus 25 ends up as steam at point F here at 125 degrees C. And to do that, we'd have to, of course, melt the ice, heat the liquid, vaporize the liquid, and then heat the steam. Now, as noted on the diagram, there are points here, significant areas of the diagram, where we're adding heat, but the temperature is not going up. So you notice wherever the green lines are, heat is being added and the temperature is increasing. But on these violet lines here, we're adding heat and the temperature doesn't seem to be going up. That's because all of the heat energy in those sections of the heating curve are trying to represent the energy input required to get a phase change. So here it would be the energy required to melt the ice at 0, to water at 0, and here it would be to vaporize the liquid at 100 entirely to steam, or to water vapor at 100. We can actually break this process up into intervals using the letters on the diagram. So for example, the interval A to B, which would be from A to B here on the diagram, what's happening is that ice at minus 25 is being warmed to ice at 0. We can signify that process on the right-hand side here by H2O solid at minus 25 going to H2O solid at 0. Now once the ice has reached 0 degrees, it begins to melt. That would be the purview of the second interval, B to C, where we have ice at 0 melting to water, staying at 0 degrees C. Remember, during these phase changes, the temperature doesn't change because all of the heat added is going in to just that phase change, getting ice to melt to water. And we can signify that on the right here, H2O solid at 0, going to H2O liquid at 0, a phase change. If we continue to heat after all of the ice has been melted to water, then we start heating the water. That would be segment CD, where water at 0 warms to water at 100. So we'd have H2O liquid at 0 going to H2O liquid at 100. We're now at point D, and now the added heat will go into vaporizing the liquid water to the gaseous form of water. This would be the interval D to E. Notice it takes a lot more heat to do that than it did to melt the ice to the liquid. That's consistent with statements we made on the previous slide. So we have H2O liquid at 100 going to H2O gas at 100, a phase change. We want to continue to heat the gas from 100 to 125, and we can signify that in interval E to F and an associated equation. Now we can proceed to calculate the total heat energy required for taking a known amount of water. We're going to say 100 grams, and that would be 5.551 moles of water molecules from a solid at minus 25 to an equal mass of steam. We don't want to lose any of the water. 5.551 moles of gaseous water at 125. Now this will require or involve calculating actual numbers for the heat energy required for each one of these intervals. And then we'll sum up all those heats to give the total heat energy required to go from ice at minus 25, point A, to steam at 125, point F. We'll do that on the next slide. So again, we're going to calculate the heat energy required for the transformation of 100 grams of ice, or 5.551 moles of ice, at minus 25 to steam at 125 degrees C. Now what I did here was throw this big table at you all at once, but I want you to notice some things about it. The first two columns of this table is simply the table I just showed you on the previous slide, where we broke the process up into the 5 different intervals. All the way over on the right on this table, you'll notice I have the calculated energy absorbed for each one of these intervals. So I have calculated energies for each interval, and then I have a total energy required for the entire process to go from 100 grams of ice at minus 25 to the same quantity of steam at 125. So what we'll do is just now look at how we got each one of these numbers, and we'll do that by kind of unveiling each one of these boxes. So how would we deal with interval AB? In other words, calculating the heat energy to go from ice at minus 25 to ice at 0. Well, one of the things we need is the temperature change, which obviously is plus 25. If we wanted to formalize that, we'd say the temperature change in going from A to B is the final temperature. That would be the temperature when we reach point B minus the initial temperature. If we do the math here, we get positive 25 degrees C, no surprises. We're also going to need this, what's called the specific heat of ice, which tells us how much heat energy is required to heat up a gram of ice and increase its temperature by 1 degree C. Things like specific heats will be given to you in tables. These aren't numbers that you need to memorize. And of course, the mass of the ice is 100. How do we get an energy? We just need to use an equation where all the units cancel out, except for units of energy or joules. So if we simply take the mass of the ice, multiply by the specific heat of ice times the temperature change, the units would cancel, grams would cancel, degrees C would cancel, and you'd be left with joules, which, for reasons that'll become obvious soon, I'm going to convert to kilojoules and put right there. We have the first interval done. Let's go to the second interval. Well, remember, this is where ice at 0 is simply melting to water at 0. It's a phase change. And remember, we said there's no temperature change when this occurs, so there's no delta T to deal with. What we need is a number from a table. In this case would be called the heat of fusion of ice, or the enthalpy of melting. Basically, it's 6.01 kilojoules per mole, and we know we have 5.551 moles of ice. So in this particular interval in the phase change, we need the number of moles. And So what we're simply going to do is multiply the heat of fusion by the number of moles, and we get the heat required directly in kilojoules, and we put it right here. Now, as an aside, note that I'm calling heat energy small q. This is pretty common to see a small q used for heat energy. Well, let's go to the next interval. Now that we have liquid water, we need to warm it to 100. And of course, the temperature change there would be positive 100. Now we need the specific heat of water, which is different than the specific heat of ice. Again, a number you would be given or look up. The mass of water hasn't changed. And so we simply need to take the mass of water, multiply by the specific heat of water times the temperature change, and we get 41.8 kilojoules. Now we need to undergo another phase change where the water at 100 is changed to steam or water vapor at 100. There's no temperature change. Here we need the heat of vaporization of water, which is 40.67 kilojoules per mole, a number you'd be given. Number of moles of water haven't changed. And so we can calculate the heat required for this process as 225.8. Now, this is by far the largest heat required so far. And if you recall from that diagram, the violet line associated with this interval on that diagram was the longest line, required the most heat energy. Now in the last interval, we're just heating steam or water vapor from 100 to 125. So we need a temperature change, a specific heat of steam. Again, you'd be given that. The mass of steam would be 100 grams. We haven't lost any water molecules, at least we hope not. And we'd calculate here the heat required for this interval is 4.6 kilojoules. If we add up all of these heat energies required for each one of these intervals, we say the total energy, heat energy required to go from a minus 25 to 125 for 100 grams of H2O is 310.6 kilojoules. Now, just as a note here, it's quite common to see Kelvin degrees used instead of centigrade or Celsius in the units for specific heat. Now, this is not a problem since the size of the Kelvin degree and the Celsius degree are identical. Therefore, for example, we listed the specific heat of water as 4.18 joules per gram per degree C. It could equally be listed as 4.18 joules per gram per K if you were recording temperature changes in Kelvin. This should not bother you, although it might, because you're used to remembering that the Celsius and Kelvin scale are not lined up exactly. They're offset by 273.15. That is true, but the actual size of those degrees are the same. They're just, the scales are just offset. And so you could see these constants given, this data given, like specific heat of water, with Kelvin degrees rather than Celsius degrees. It is possible to calculate the energy absorbed for any specific portion of the heating curve. For example, the diagram on the right is a reproduction of the heating curve from the previous slide. Suppose we didn't want to calculate the energy going all the way from point A to point F, but rather we wanted to know the energy absorbed when 100 grams or 5.551 moles of water at 70 degrees, this means we're starting as a liquid at 70 degrees, is converted to steam at 110 degrees. Well, we can do this, and in doing so, we don't need all of the information that we used before. So in this box here is all of the information we used before, only we've grayed out what's not needed. So in other words, we don't need the melting point of ice because we're not dealing with ice. We don't need the specific heat of ice, and we don't need the enthalpy of fusion or of melting. So we can split this process up into just 3 intervals or 3 segments. The first would be starting at this X, this brownish red X, going to point D, and that would simply be water starting at 70 degrees C and warming to 100. The next interval, D to E, would be the vaporization of that water. So it would be water at 100, vaporizing to steam at 100. And then in the final segment, E to this orange X, we just need to calculate the energy needed to heat the steam from 100 to 110. So let's go back to the first interval, X to D. This is where liquid water at 70 is simply heated to liquid water at 100. So the temperature change is obviously 30 degrees in this interval. We'll use the specific heat of water here, and of course the mass of water, and we'll calculate the heat required to go from X to D, the mass of the water times the specific heat of water times the change in temperature. Units cancel here, and in this example we're explicitly showing the cancellation of the units, leaving joules, which we can convert to kilojoules, and we'll put in this column right here. For the interval D to E, we've got liquid water at 100, vaporizing to water vapor at 100. This is a phase change. There's no temperature change. We simply need the heat of vaporization of water, and of course the number of moles of water. And we calculate the heat involved in this process would be the heat of vaporization times the number of moles, showing unit cancellation. We get 225.8 kilojoules. That number should look familiar. For the final interval, we simply have water vapor being heated from 100 to 110, 10-degree change. Here we'll need the specific heat of steam, and of course the mass of the steam. So we have the heat absorbed for this process be the mass times the specific heat of steam times the change in temperature. We do some unit cancellations, and we get 1.84 kilojoules. We add up the energies needed for these 3 intervals, and we get a total of 240.2 kilojoules. How about if we look at a substance other than water? Suppose we want to know how much heat energy is required to convert 322.4 grams of acetone, which has a molar mass of 58.08. That would be 5.551 moles of acetone. I picked this mass exactly so it would be the same number of moles of acetone as water that we used on the previous slide. And we want to take it from the liquid form at 26 degrees C to a gas at 66. The boiling point of acetone is 56.05, and we have its heat of vaporization and the specific heats of the liquid and gas forms Again, all numbers we could look up or would be given. So for what it's worth, as I alluded to just a second ago, this question makes an attempt at comparing the heat energy necessary to take acetone through a phase change similar to that done with water on the previous slide. The similarity is that both situations involve taking the same number of moles of compound from a liquid form that's about 30 degrees below the boiling point to a vapor that's about 10 degrees above the boiling point. We can set up this calculation quite easily, break it up into 3 intervals. Basically, in interval number 1, we have the liquid form of acetone being heated up from 26 to 56.05, its boiling point. We have the specific heat of acetone, the temperature change, and the mass. So therefore, we can calculate the heat energy needed to get this done. And it's 20.9 kilojoules. The second interval involves a phase change where acetone in the liquid form at its boiling point is changed to acetone in the vapor or gas form, still at its boiling point. We use the heat of vaporization given, the number of moles of acetone. We can calculate the heat required here in this interval, and it's 173.7 kilojoules. In the last interval, we simply have acetone in the vapor phase being heated from 56.05 to 66 degrees, and we can calculate from the temperature change and the specific heat of acetone vapor the heat required to do this, and it's 4.14 kilojoules. We add up these numbers, we get 198.7. Now let's compare water from the previous slide and acetone on this slide. Now the overall heat energy required for acetone to transition from a liquid to a gas in a comparable temperature range is less than for an equal amount, meaning equal number of moles, of water. Again, it appears that the overall heat energy needed is less than what was needed for water. Now this is, just to remind us, the water required 240.2 kilojoules. Now this is consistent with our previous conclusion that the intermolecular forces in acetone are weaker than those in water. We talked about that in a previous module. Now a closer look at the calculations on this slide and on the previous slide reveals something interesting, and that is the largest difference between acetone and water seems to be in interval number 2. So for water in interval 2 required 225.8, acetone only 173.7. And in this phase change is where liquid molecules are actually separating from each other to form the gas. And remember, that's how we visualized the effects of intermolecular forces. It makes sense that water, which has hydrogen bonding, would be more difficult to separate into gaseous molecules from the liquid than would be acetone molecules, which, though polar, do not hydrogen bond to each other. Now, there is something else we need to point out here. Well, we don't have to point it out, but we're going to, is that it's actually acetone and not water that appears to require more energy to cause a temperature increase both before the boiling point. Notice water took less energy to get to the boiling point, and after the acetone is vaporized. So to heat up the vapor, after vaporization required less energy for the water than for the acetone. Well, is this last point something you should be concerned about? No, not really. I just thought it should be pointed out in the interest of full disclosure.